Okay, here we have quiz 19.1, balancing chemical reactions. And the first question is to balance a few reactions under acidic conditions. So what you're given here is an unbalanced reaction. It's not just that it's missing the coefficients, but that it's actually missing some reactants and or products. And so it's going to be quite a feat to balance this. Let's start by writing it out, and I'll write small because we will need to write a lot down. Yeah. So H2O2 is hydrogen peroxide. ClO2, chlorine dioxide. That's the chlorite ion. And oxygen gas. So at this point, I'm going to see if I can switch over to show the process of how to balance a chemical reaction. Well, I want my version of that as well. Okay, so the first step is to balance any elements other than hydrogen and oxygen as usual. So we have a chlorine here, but it is already balanced, so we can skip that. Then we're going to assign oxidation numbers to any elements in the equation. So if the oxygen here in hydrogen peroxide is a bit of an exception to our normal rules. Oxygens normally take a 2- whenever they're in the context of a chemical compound. This is a peroxide, and that means that the oxygens will take a -1. You could see a clue of that by the fact that it's bound to hydrogen, which takes a +1. Hydrogen cannot take any higher oxidation number than +1 because it only has 1 electron to lose. And so the hydrogens are +1 and the oxygens must be -1. Here we've got -2 for that oxygen. There are 2 of them, so that's a total of -4, so that chlorine is +4. Here we've got the same -2, -4. But the chlorite ion has an overall charge of -1, so that chlorine is +3. And the oxygens here are 0. So we're not going to focus too much on how we've got oxygen everywhere, and we could go crazy trying to sort everything out from the perspective of oxygen. Let's instead look at the chlorine. So the chlorine has been reduced from +4 to +3, and some of the oxygens remained the same at -2, but some of them have been oxidized to go to 0. And so we need to modify the coefficients if necessary to balance the electron exchange. That means that this chlorine has gained 1 electron. These 2 oxygens have each lost 1 electron, and there are 2 of them. And so to balance this, we're going to need to put a 2 in front of the chlorine dioxide and the chlorite ion, so that there's a total of 2 electrons that are lost by the oxygens collectively in the hydrogen peroxide, and 2 electrons that are gained by the chlorines in the chlorine dioxide. Okay, 1 second, I gotta scroll down. Okay, now we're going to balance any missing oxygen atoms by adding water molecules. I have 1, 2, 3, 4 oxygens on the left, 1, 2, 3, 4 oxygens on the right, and so there's no problem there. And then we're going to balance any missing hydrogen atoms by adding H+ ions. And so we are missing 2 hydrogen atoms here on the left and none on the right. So we will add plus H+, and there are 2 of them on the product side. Whether you put them on the reactant side or the product side depends on where they need to go in order to balance. And of course, we could do H3O+, but that would throw our oxygens out of balance and things. So this is one case where it really is just easier and simpler to use H+ to represent acid instead of the H3O+. And then lastly, we'll want to verify that all atoms and the overall charge are balanced. And I think the overall charge is the only new part here. We have purely neutral species on the left, so their overall charge on the reactant side is 0. And then we have 2 chlorite ions, which add up to a total of -2 charge, and 2 hydroniums here that will add up to a total of 2+. And together, collectively, they are 0, so that charge is balanced. Okay, give me a sec, we'll switch back to the quiz. And look down at the next one. I'm going to leave some space here because we're going to be balancing it under basic conditions soon as well. Hold on, sorry. All right. So this next one is Fe2+ aqueous plus MnO4- aqueous. That's called permanganate ion. And we'll leave some space here. And we'll have Fe3+ aqueous plus Mn2+ aqueous, the permanganate ion. So we'll run through those same steps. We'll balance any elements other than oxygen. In this case, they're all balanced, and that's fine. And then we're going to assign oxidation numbers. So we have a 2+ and a 3+. Pardon me, that's just chalk dust, not COVID-19. And then the manganese will be 2+. Those monoatomic ions are all very easy to assign oxidation numbers. Then here in the permanganate, oxygen is a -2. There are 4 of them for a total of -8. And the manganese balances that out, so it'll be +7. And we can see that the iron has been oxidized. It's lost 1 electron going from 2+ to 3+. The manganese has been reduced from +7 to +2. That means it has gained 5 electrons. And so in order to balance those out, we need to have 5 irons. 5 iron here, and 5 irons there. And now we're going to balance out any missing oxygen atoms by adding water molecules. I have 4 oxygens on the left, and so I better add 4 waters over here. And now we balance the hydrogens with H+ because we're under acidic conditions. And so there weren't any hydrogens before, but we just introduced 8 new hydrogens, so we'll have to put 8 H+ aqueous ions on this side. Sorry, just double checking my work here. And we can see that the charges are balanced. Now we've got 10+ from the 5 irons, and then a 1-, now it's at 9+, plus the 8. It's a total of 17+ on the reactant side. Let's see what's on the product side. 5 times 3 is 15, plus the 2 from the manganese, and water's neutral, again 17+. So the charges should balance as well as the elements themselves. So question 2 says to balance the same reactions in basic solution. Let's switch back over to our notes and we'll show you how we balance in basic solution. There's just a few extra steps, right? So we'll start with the top one. For each H plus ion, we're going to add an OH to both sides. So we'll have 2 OH minuses on this side, and we'll add 2 OH minuses on that side. And then we will combine the H pluses and the OH minuses to form waters. So these become 2 waters. And then we're going to cancel out any water that appears on both sides. In this case, there was no water anywhere, and so our base balanced hydrogen peroxide reaction is H2O2 aqueous plus 2 ClO2 aqueous plus 2 hydroxide is going to form 2 ClO2 minus 2 chloride ions plus O2 gas plus 2 waters, H2O liquid. And so we see now we have base appearing in the final balanced reaction instead of the water. Instead of the H plus. And now let's balance the next one in base. We'll do the same procedure. We'll add 8 OH minuses to both sides. We will combine these together to form water. So we have 8 waters. And then we're going to cancel out waters that appear on both sides. And so we have 8 waters right here and 4 waters right there. What we can do is eliminate the waters on the product side altogether and cancel out 4 of the waters on the reactant side. And so our final base balanced iron 2 plus with permanganate reaction is 5 Fe2 plus aqueous plus permanganate, and then O4 minus aqueous plus, now we have the 4 waters, 4 H2O liquid. And that is going to form 5 iron 3 ions plus a manganese 2 plus ion. And we have those 8 hydroxides now on the product side. And that is the balanced iron 2 with permanganate reaction. Okay, we're going to switch back one last time. So question 3 is a titration problem. And it has to do with iron nitrate, where we see that the iron is in the 2 plus state, with potassium permanganate. And so it's actually this reaction we have right here, the iron with permanganate in acidic conditions. Well, we have the fully balanced chemical equation right there. We're not going to actually need every bit of it. And I want to point out that whether it's balanced in acid or in base, you get the same ratio. That is that 5 Fe2 pluses to every 1 MnO4 minus. That is the stoichiometric ratio between iron 2 and permanganate ions in both of these reactions. So I can go ahead and erase them now. And you can go ahead and do titration problems with redox reactions the same way you do titration problems with acid-base reactions, and throw in an extra factor to account for the different stoichiometries. But that can get maybe a little bit complicated. When do you multiply by 5 or divide by 5? And in order to keep it simple, I like to solve these sorts of problems just as one big long dimensional analysis problem. And so what is, looking at our problem there, the number that we want to start with is the amount of titrant added. That is the measured amount that is specific to this trial of this particular experiment, specific to this problem. And so we're going to start with that, 13.65 milliliters. It's iron nitrate technically, but the iron 2+ is the only ion we care about. And because this is a dimensional analysis problem, I'll just draw a big long line there. We'll see how much of it we need. And the concentration, oh, hold up. I'm sorry. It's 15.65 milliliters of the permanganate solution. That's MnO4 minus. Okay. Right. The permanganate solution is the titrant. That's what we used 13.65 milliliters of. And that concentration of permanganate says that there is 0.103 moles of permanganate ion for every 1 liter. Now we have milliliters here and liters there. We're going to later divide by milliliters in a way that will make it so that this is not a problem. We don't have to waste time converting your milliliters into liters for this to work. And in fact, it's much simpler if you don't. Here we'll use our ratio, that 1 MnO4 minus is going to be equated to 5 iron 2+. And then finally, what volume did the iron 2+ ions occupy in the unknown before the titration started? That's our 25.00 milliliters. And so you see the milliliters will actually cancel, and the units we're left with are moles per liter, or the molar concentration of iron. Permanganate cancels out, and we're left with iron moles per liter. And put this in your calculator, and what you end up with is 0.281 molar FeNO3 2. That is the molar concentration.